Okay, ooh, it froze for a second. That was scary. Yeah, okay. All right, so, okay, so let's go ahead and kind of pick up from where we left last 2 weeks ago, really, well, not 2 weeks ago, last Wednesday. So, because Monday was Labor Day. So we were just starting to introduce this idea of recurrence relations, right? Because what we did was we basically were talking about time complexity and analyzing code, and that was your homework assignment and whatnot. And I think the homework assignment is due sometime soon. I'm not sure, but you were looking at iterative code, right? Procedural code, that kind of code, right? And so basically, that code is cool and somewhat easy to figure out the time complexity. Most of the time, unless the code is really weird and poorly written, I suppose, because you can just look at the for loops basically. When it's a function calling out the function, you have to kind of figure that out, but for the most part, it's relatively straightforward. The issue comes in when you have recursive code, because recursive code is not as easy to just look at and be like, well, this is what the time complexity should be because this is how many times it's running, because you can't know that for sure. There is some recursive code that's really straightforward as to how it works. If you think about something like binary search, binary search is going half, right? So that's the powers of 2, that's logarithmic. Okay, that's a little bit intuitive. However, not all recursive code is like that. So even though a lot of the examples that we'll do in this class are somewhat intuitive and you're like, well, we don't really need this, we're preparing you for ones that may not be, which are definitely out there. And you're going to revisit this in 477 in algorithm analysis class. So even if you don't get it too well right now, you will hopefully get it by then. And so normally, I put a question on the test, on the midterm at least, on this stuff, and like most of the time people get it wrong, and it's very sad. But I think at least I prepare them for 477 when they go over. 477, I was just talking with one person that's taking it right now, and a lot of that class is reviewed from 302, so it's a good thing. It helps you reinforce that stuff, okay? So anyways, recurrence relations, used to determine the runtime of a recursive program. And so the example I was giving you is that we are sort of representing the time it takes for a recursive piece of code to run by calling this T of n, okay? And what this T of n means is that the n is going to represent how many iterations, per se, you're going to be doing this, okay? Is there a big lag on the thing? I hope there's not big lag. I will check. I think I have low latency mode enabled, but hopefully not. I was 5 seconds when I checked earlier. But yeah, so when you say something like T of 1, we're saying that one iteration of this, not iteration because it's recursion, but like one run of this function is going to take one operation or 1 second. Okay, just think of numbers like seconds for now. Okay, 1 second. When I say T of 2, well, that means that we have to run this basically, you can think of it like twice, okay? But because it might take different amount of time based on the number, we represent it as saying, well, T2 is going to take whatever T1 takes plus some extra time, which is whatever this run takes. So that is why you see there T1 plus 2. The T1 represents however the first one takes, which we said 1, plus 2. So what we're saying is that the final case, or the base case, T of 1 takes 1 second per se. But T of 2 takes whatever T of 1 takes plus 2 additional seconds. Meaning that T of 2 is actually taking a little bit longer than T of 1, regardless of however long T of 1 takes, okay? So really, when you have something like T of 2, it takes whatever the first one takes plus 2, which is 1 plus 2 is 3 seconds, okay? Then T of 3 takes whatever T of 2 takes plus 2 more seconds, okay? So we already said that T of 2 takes 3 seconds, so really we add 3 plus 2. And then you can see the pattern that if it was T of 4, then it would be basically whatever T of 3 takes plus 2 seconds, which would be 5 plus 2, 7, okay? So the formula that represents what I was just saying is what I wrote up here. So T of n takes whatever T of n minus 1 takes, because you have one less step to do, plus whatever the time takes. So really, what the arrow is pointing to here is really how long this step takes. But to find out the total number of steps, you're saying, well, this plus whatever the remainder takes, okay? So you always think of recursion like this. You do a piece of work and then you have a leftover, right? And you think of it that way. Do this piece of work now plus the leftover. And then you look at the leftover and you split it again into a piece you're doing now plus the leftover of that. And the idea is that every time that leftover starts to become smaller and smaller and smaller until you get to one item left, which is your base case, okay? So hopefully that makes sense, and this is how recursion works. So the question becomes how we can figure out how long it takes. One way to do that is kind of what I did here. If you get like an actual number of the number of steps you gotta take, so T of n is equal to 3, then you just literally plug them in like I did, which is cool. You can plug it in onto any formula and kind of just grind it out. That would be the equivalent of you like drawing like some kind of tree, or like literally figuring out the recursion by hand, like some Fibonacci or something. And that works great for like testing your answers or sort of getting an idea of how the pattern goes. But it doesn't give you the general case of the solution. So you can't use that as proof that you are correct, right? It'll give you intuition like, okay, this is going in a linear time or this is going logarithmic time, but I don't have the mathematical proof for that. The recurrence relation and solving that is going to actually give you the mathematical proof that you can then say, okay, this is proof by math, like this is now has been officially proven, so it's no longer an estimate. And so that's the tricky part, trying to figure that T of n, okay? So I'm gonna show you 3 ways to do it. One of them is it's called a tree, which I'll kind of just show you quickly, but we won't cover it much. Then I'm gonna show you this simple, well, first of all, I should say, there isn't one way to solve all recurrence relation problems. Think about like differential equations if you ever taken that class. Like, there isn't one method that will solve differential equations. Like, there's methods that will solve a certain group of them, but not all of them, right? So you got to approach them with different like methods. Like, there's like Laplace transforms, or there's like very simple like, you know, plug in things to solve like a problem if it's relatively straightforward and whatnot. But there isn't like one way to solve it where you're like, okay, if you do this method, you will solve it every single time. The same thing with recurrence relations. There isn't one. There is something called the general master theorem, which does help to solve a lot of cases, but even that is limited to a certain group of recurrence relations, which are the most common, actually, which helps out. So if we have time, I'll show you a little bit of the master theorem. If not, then 100% is shown in 477, okay? So you can think of this more as like an introduction to recurrence relations than as like showing you the exhaustive way of solving them, okay? So with that introduction out of the way, let me go ahead and show you the most simple example I can think of for this recurrent relation, which is kind of what I was doing here, okay? So I'm just gonna write this out that I have here. Okay, so we have the following recurrent relation, which is the one that I wrote last time. So let me make this a little bit bigger. Actually, over here, since this is video 4. So solve the recurrence relation and give the asymptotic complexity, okay? And the problem is going to be the one that I showed last class, or that I was just showing a second ago. Okay? And just like with any recursion, you always have a base case. And if you don't, what I said last time holds, which is make an assumption that it's either equal to, that it's T0 or T1, and that it's equal to 1 or 2 or whatever. But in this case, you are getting something different, which is a 2, okay? But you can make that assumption if you don't get one, that T of 1 or T of 0 are going to be equal to 1, okay? That's one assumption you can make. So if you ever get a problem and you don't get that, you can ask for it, but if nobody answers it or you don't know, just make that assumption. It's okay. It's not really going to mess it up too much either way. So, because they're constant numbers at the end of the day, right? And if you remember with asymptotic complexity with all the different tiers of this, like this stuff here, constants all the way at the bottom. So it doesn't really make a difference what that number is, as long as it's a constant, which it will be. Okay? So the first thing that I want to show you that you can do to figure this out is, remember, you can flip things around with an equal sign. So if you have something like A is equal to B, you can say something like 2A is equal to 2B, right? You could also say 1/2 A is equal to 1/2 B, or you could even say A times C is equal to B times C. You could do that. You could also say A squared is equal to BA, right? Because you're just multiplying A on both sides. So you can always do these properties where you can just add two things to each side. So just remember that from math. And then also remember that if you have something like this, 2 plus A is equal to B, or here, 2 plus A is equal to 5, that you can then use that to flip locations of variables. So for example, this cancels that, so then you get A is equal to 5 minus 2, which is equal to 3, right? Okay, so hopefully you all remember that. I mean, like, I'm reviewing this because, like, I assume you all know this, but it might have been a while since you do, like, basic algebra. So yeah, but this is basic algebra, so, like, low-key, I mean, you should have learned this in, like, middle school or something, right? So yeah, okay, so anyways, so using that property, we can flip the T of n minus 1 to the other side, right? So we can say something like T of n minus T of n minus 1 is equal to 2, right? So that's how I get that, okay? So just making sure that I show that there, all right? So yeah, just remember that for now, and let's sort of plug in all the numbers starting from the bottom. So this is going to try to solve it from the bottom up, okay? So from like 0 all the way to n. So there's two ways you can go about this. You can try to figure, you're ultimately trying to find a pattern, okay? Trying to find out how this is going. So you can go from 0 to n, or you can go from n to 0. First, I'm going to show you from 0 to n, and then later on in the next example, with totally different approach to do this, then you will see the n to 0, okay? So because we're going from 0 to n, then let us try to plug in our base case here. So our base case is T of 1 is equal to 2, right? So that means that n has to be equal to 1. So if I do that, if I plug that in and say T of 1 there, then this becomes T of 1 minus 1, which is 0, right? And so that becomes that. And then this has to be equal to 2, okay? Because of this, and because we know that T of 1 is equal to 2 from literally our base case here, then I can plug that in into this equation right here and say 2 minus T of 0 is equal to 2, right? With that, I can then flip that to the other side. So I can say 2 is equal to 2 plus T of 0 by adding 2 0 to both sides. And then I can take away the 2 by subtracting it, and I end up with T of 0 equal to 0, okay? So I have now just solved how long T of 0 takes, okay? Just to kind of refresh your minds on how basic algebra works, okay? So I have two cases now. I have the case of T of 0, and I have the base case of T of 1, right? Okay? So, doing that, let us say that I want to figure out, since I'm working from my way up from 0 to n, the next thing after 1 is 2, right? So let us try to plug this in using this here. So let me just copy and paste it a few times since we're going to use it a bit. Let us copy and paste this a few times and plug in T of 3, T of 4, and so on, okay? So actually, what I can do is I can just copy paste the copy paste, right? Don't code like that. All right. So let us plug in T of 3, or T of 2 this time, which means n is equal to 2, and then this one's going to be n is equal to 3, and then this one's going to be n is equal to 4, n is equal to 5, and so on. Okay. So with 2 there, that means that I have to literally plug in here a 2, and then if I do that, then 2 minus 1 just becomes 1. Like that. And then over here, and we know what that is, by the way. We can plug in, that's a 2, right? But we're not going to plug it in yet. Not yet. Okay? For this one, on the other hand, this is equal to 3. And so this becomes 3 minus 2, which is equal to 2, right? So what is that going to be equal to? Well, that's going to be equal to whatever t of 2 is equal to, which we can figure out if we solve the one above it. Which we could plug it in, because we can say this is equal to 2, and then it becomes t of 2 minus 2 is equal to 2, which basically becomes 4, right? Because you add 2 to this side, so t of 2 is equal to 4. However, I am not going to be doing that right now, okay? But I could do that. I could literally plug it in and work my way up if I plug in every single one. But then I'd be working for infinity, because n could be a really big number, okay? So I'm not going to do that yet. I just wanted to do it for one, just to make sure we're on the same page. I'm not going to do that yet. I'm just going to plug them in, okay? Because I want to show you something that's going to happen here. The same thing for t of 4. So 4 minus 1 becomes 3. T of 5. 5 minus 1 is 4. And so on. I believe that you should be noticing by now a little pattern on how this is going. So if I skipped a couple of steps now, and I said, I don't know, n is equal to 10, what would that be equal to? Well, that would be t of 10 minus t of 9 equal to 2, right? So I think you see the pattern there. And please correct me if you don't see it, okay? So I can generalize and say, well, we know that t of n is literally going to be t of n minus 1. So then what if we said like t of n were, minus 2? That's almost n, but not quite n. So like if n was 1,000,000, this would be like 999,998, right? Well, if that's the case, then the t of n here would be t of n minus 3, because it's, whatever this is minus 1. So it's like n minus 2 minus 1, right? And so because of that being the case here, then this does become n minus 3, okay? And if that's equal to that, then t of n minus 1 is going to be t of n minus 2 here, and then t of n is going to be t of n minus 1, okay? So what I have done at this point is figure out a pattern that is appearing itself, which is literally just like, well, one side is the other minus 1, right? Okay, great. So now I want you to notice something. What I'm doing here is I am trying to list out every single recurrence that is basically going. So like if n is equal to 10, then I have to literally add all steps. Or here, if n is equal to 5, to figure out how long this program takes, technically speaking, I have to add all of these, right? Whereas if I want to figure out how long the n takes, then I would have to add all of these, right? So why don't I just try to add them right now? Well, I figured out y equals to 2 here. We can see that here is just 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2, right? How many of those are there? Well, n here is literally equal to n, and at the beginning n is equal to 1, right? Or 0 if we do it start from 0, but 1 is better, okay? This is going from 1 to n, so there's n of them. So because there's n of them, then we just multiply n times whatever the number here is, which is a 2. So this becomes 2n, okay? On this side, it's a little bit tricky to add all of the cases here. We have to literally add them all together. So for example, if we were trying to figure out just the ones in the pink circle, or purple circle, I'm not sure what color that is. If we're just trying to add all of these together, we could do that by putting a plus sign, like this, right? We already added these, so let's just ignore that for now. And then, if we want to make it prettier, we could literally put them side by side, I suppose. But that's not really important. But the point is that I want you to see what happens to these terms when I do that. Okay? So like, when I add this together like this, and then I add this one as well. okay? So I'm adding all of this together, all right? I just can't fit it all in one line. Well, guess what? Here I have a T2, but then over here I have magenta. Is that magenta? Okay, interesting. I have a minus T2. Those two cancel out, right? Because like we know, what is T2? What did I say it was really quick? T2 was equal to 4. So really this is saying 4 minus some stuff, minus 4 again. So the 4's basically cancel each other out, right? So the terms cancel each other out. In addition to that, let's switch over to, you should do the Bob Ross thing. We're going to switch over to water blue, okay? So we switch over to water blue here. T3 here is being subtracted over here. So they're canceling each other out again. So those two terms cancel out. And if we switch over to earth brown, this T4 gets canceled out by this T4. Okay? So it turns out that really what you end up with when you go all the way to just 5 is just T1 plus T5. Because all the other terms cancel out. Okay? That is something that is going to happen regardless of what number we're going up to. So in here, this term and this term cancel out. This term and this term cancel out. This cancels out. This would cancel with something else here. And then the one right before this, so this would be like Tn minus 3, would cancel out with this Tn minus 3. So they all cancel out kind of in a zigzag pattern. And this one cancels out with this one with this one. So you only end up with two terms, regardless of whatever size you go to. So you only end up with this Tn and this minus T1. Okay? So ultimately, and again, this is not something that just magically happens. This is like something you have to kind of detect. You know, it's not like there's an easy way for me to tell you like, oh, well, this always happens. This is on a case-by-case basis, really. Well, this ends up being with Tn minus T1 is equal to 2n. Okay? And so, because we know what T of 1 is equal to, because that's literally our base case, that's equal to 2. So this really becomes T of n minus 2 is equal to 2 of n. If we flip the 2 to the other side, like that, then it ends up being that the solution to our recurrence relation is 2 of n plus 2. Now, how do we know that we solved it? Because you're like, wait a second, we still have all these n's and stuff. Right, but we only have one term that has a t to it. And then it's giving us a non-t side. So whenever you have the equal signs and you find something here that does not contain another t of n format, that's your base case. Because I mean, think about it this way. It's literally that code. If you see this t with parentheses, it's a function call, which means you have to do more recursion, which means you're not done. But in this case, there's no more recursive calls. And so that's how you know you're done. Okay? So you're like, cool, great. Now, what do I do with this 2 of n plus 2? Well, very good question. What do you do with this is you go ahead and, oh, by the way, did I screw up? No, I didn't screw it up, I guess. But technically speaking, if I had here my t of 1 minus t of 0 case, then I would have canceled that out. But that's fine. We can ignore that for now. Okay? So if I end up with something like this, t of n here equal to 2 of n plus 2, that's what I put up here, right? Yeah. So it turns out that that is your asymptotic complexity. That's your big O, whatever is in there. So your big O is literally 2 of n plus 2. Okay? And furthermore, because these are just constants, then you can say that this 2 of n plus 2 belongs to just O of n. Okay? And if you remember the big O definition, in fact, let's just really fast scroll all the way up to there and copy paste it. Big O right here. So copy this. And scroll all the way back down. See, we've written a lot of stuff. Like I checked and like last semester, I think I wrote like 200 and plus pages by the end of the semester. We're already on page 44, by the way. So yeah, it's a lot of writing. It's kind of cool. So, okay, so that's our big O, right? G of n as n goes to infinity, where f of n is less than or equal to mg of n. And this g of n is the one that we sort of solved technically. And so what we're saying here is that the g of n is just going to be a 2. The m is equal to 2, which is being multiplied by that. And then this plus 2, to kind of avoid that being an issue, we can just make the n0 kind of be equal to 2. And then that will avoid issues with the growth rate that is not okay. Okay? So a simplified version of doing all of that is you can just write the following, and then I will understand what you're saying. This is called a certificate. And you can plug this in as saying t of n is less than or equal to c times n. And that c is like that m that you think about, okay? And again, this is just a constant, so it's not that big of an issue here that we have this plus 2, okay? So yeah, that is basically the solution to the simplest example that I can think of with a recurrence relation, okay? So you get rid of all the t's except for the left side where you have just a t of n, and then you this actually would be your theta, because that's tight. This is literally saying that this is the exact line. Like this specific problem happens to have a really nice and clean line that we can actually say, well, this is not an approximation anymore. This is literally the exact line. So this actually would be your theta, which happens to also be your big O and omega, because remember the theta is like the combination of both. So yeah, it's tiring to write that many pages. You know, I don't notice it. Like, I don't even know we're on page 44. I assume we're like on page 10 or something. But no, because think about it. It's like 40 hours of class throughout the full semester. So, you know, it's okay. If anything, it's more tiring writing on a real whiteboard because you gotta like stretch out and whatnot. Like your hand gets tired. Especially if the classroom is like weird and has really tall whiteboards. But you want to maximize the space. So yeah, this is actually a good example of a theta because this is literally the exact number, okay? Not all the recurrence relations are this pretty though. I will warn you about that. But okay, this is one way of doing it. Again, what we did to summarize is we started out from 0 and we were going to n and we try to find a pattern. And we found a pattern that usually happens where things cancel each other out. So we basically added them all together. On the right side, it was 2n. On the left side, all the terms cancel out except for the first term, which happened to be the base case, and the last term, which was t of n. So we ended up with this because we know the base case takes 2. Then this became t of n is equal to 2n plus 2. Once we do that, then we can say, because of the definition of big O and big theta and big omega, that 2 of n plus 2 belongs to the class of O of n. And the proof to that is by saying that there's a constant, this m or c, which is equal to 2, and this will work for all n being greater than 1. Won't work for 0 because of the y-intercept, okay? And so, yeah, that's pretty much all there's to it. You can, if you want to make this feel better, you can do the plus c there. That way, the y-intercept with the plus 2 doesn't cause issues. But I will understand it either way, okay? So this is how you figure out your theta, or in this big, in this case it's a theta, but also your big O. Okay? In fact, I would say that the theta of this is 2n plus 2, and the big O is just a n, like that. That would be a good way of saying it, okay? But on like a test or something, make sure you show your work so I know that you simplified that. What do you say about the certificate? The certificate, it's just basically it's like a simple proof to say that your solution will work with this specific scenario by plugging in these numbers for the constants. So for this m in the definition, you're just saying, well, as long as this m is equal to 2, what I said holds basically. So that's more than enough for that. Okay? So yep, that's a really simple example. Yeah. The ERC quotes on proof. Yeah, it is very ERC quote. Okay. Will there be multiple choice question? There's no multiple choice questions on the 3021. It's all because it's a lot of drawing. Like we haven't drawn yet, but don't you worry, we will start drawing pretty soon. So yeah, this is math, but then we go into art. Okay. So this one's really nice because it's simple. I think, frankly, whenever you see, this is a good, it's always good to kind of intuitively kind of see what the answer should be, because then you can kind of guide yourself in that direction. Obviously, sometimes you can be misled, but a lot of the times you won't. When you see something like this, where you have a recurrence relation is this format. If this is a simple addition or subtraction, that tends to hint to you that this is a linear relationship. When you see something, and a minus here as well. Actually, correction. The +2 here is very irrelevant, but if you see addition, then yes, it probably is linear. But really what matters is here as well. When this is decreasing by 1, it means that every single step that you do decreases by 1. So this kind of like the equivalent of like a for loop where you have like an I++. That's kind of the same thing as saying n-1 here, okay? If you see in there a division, then it's probably going to be logarithmic. If you see like some square stuff, then that's when it gets hardcore and you go to like either exponential or powers, quadratic and whatnot, okay? Because this is really just a constant. So this could be like a plus 100 and whatnot. So those are some things to kind of give you a hint as well. And yeah, merge sort and quick sort do require a lot of writing at least, because you got to show all the steps. Yeah, that'll be fun. Okay, let's do another one. This one we're going to use with a different method. This one we're going to use a method that goes from n to 0. So before we were going from 0 to n, that works a lot of the cases that are simple, but not really for more advanced cases. This is a case where it might work better to go from n to 0, okay? So for this one, the problem we're going to be looking at is going to be t of n is equal to 2t n divided by 2. So remember what I said, that's already a hint to you, like, there's some logarithms involved in there. It might not be just logarithmic because we have this 2 here, which makes things more interesting, but there's definitely some logs that are going to be involved, all right? Lots of trees and lots of logs. Okay, base case. The base case, we're just going to pick 4. Okay? So, great. If we try to do the other method, you know, we really wouldn't get anywhere, because if we let's just try it. Let's just try the other method for now. Let's just try and plug in t of 1 here, because we know what the base case of that is, which is 4, right? So 4 is equal to 2t of 1/2 plus 4 n, right? Which I guess, yeah, we don't. By the way, this is a good point. We have that 4n there, right? And we're plugging in a 1 there, so that means that n has to be equal to 1. So we could, in theory, just say that this is 4, because n is equal to 1, okay? That's important too, also to realize. So if we do this, we can see that 4 is equal to 2t 1/2 plus 4. So we can get rid of this 4, and this becomes a 0. And then we can divide this by 2, which just literally does nothing. So we can kind of get that t of 1/2 is 0. But that kind of made it worse, because we're trying to get to n. We're not trying to get to 0. Like, this actually became smaller, right? So you're already kind of like, okay, this doesn't look too good. So you can see that this isn't really going to work out. Like, the previous method won't really work out well for this. It might, but it just looks too hard to do. Okay? So the method I'm going to show you, which is going to go from n to 0, is called the build and expand method. Okay? At least, I mean, this is not like a very official term, but I think you'll find it on Google if you Google that. And then do like recurrence relations or something. If you Google that, you'll find some examples probably, okay? So the idea here is kind of what we're doing before with plugging it in, but starting from the n side, not from the 0 side, okay? So we're not even going to touch the base case for now. We're gonna leave the base case like away. We're gonna forget about that for now, okay? So what I wanna do is say, okay, I'm starting out from n, so if I want to solve this, the first thing I should do is figure out what this is equal to, what this t of n divided by 2 is equal to. Because if I know what the answer to that is, if somebody, if like, so, you know, I had like some divine illumination and somebody just came to me and said like, yo, this t of n divided by 2 is equal to 42. and if somebody just told me that, I'd be like, oh, okay, cool. Because now I can just be like, well, this is equal to 2 times 42 plus 4n, which would be equal to 84 plus 4n. And be like, hey, cool, this is actually linear in this case. And I'll be done. I'll be like, yay, you know, GG's and whatnot, right? But unfortunately, I don't have such divine elimination. And if you did in your test, then I would be like, let me go check if you cheated or use check. But yeah, okay. So because we don't have that, we're going to have to do things the old-fashioned way, which is to work them out. And so let us try to figure out what this T of n is equal to 2. Oh, sorry, what this T of n divided by 2 is equal to. Not equal to 2, but equal to. Different things, okay? So what I'm going to do is I'm going to split my page into 2. And this is the build section. And this is going to be the expand section. And what I'm going to do is I'm going to write over here what I started out with. T of n is equal to 2 T of n divided by 2 plus 4n. And because what I'm trying to solve is basically this T of n divided by 2, I'm going to expand that term over here and see what it would be equal to. But how do I do that? How can I expand that? Well, I can expand that by taking the previous term and plugging in numbers that would work there, okay? So I know what the formula looks like when it's just T of n. However, in this specific scenario, I'm trying to figure out T of n divided by 2. So that you get what I'm saying, let me just write that down twice here. So I have this here, okay. In fact, let me move this for now, down here. So I have this. I know that this works because that's what I was given, okay? And I'm going to just, actually, I'm going to rewrite it because I want to make it a little bit bigger. T of n equal to 2t n plus 4n. Okay, that's better. All right. So I know this is valid because that's what I was given at the start. But I'm trying to figure out this T of n divided by 2. Well, look at these. Like literally look at this and then look at this. The only difference is this divided by 2 part. So why don't I just throw it in? Well, if I do that on one side, I have to do it on the other side. Which means that on this side here, which by the way, I put n, but it should have been n divided by 2. I don't want to confuse you, so let me start over. So that's the start. That's what I have. So what I want to do is divide it by 2. So I divide by 2 here. So what I do to one side, I have to do to the other side. Again, from algebra. So I have to divide this 2 by another 2. Right? Like that. What that is equal to is the same thing as if I did 2 squared. Right? Technically speaking. And so I also have to do that to the end here. And divide that by 2. Okay? Because I'm dividing all of the ends by 2. So I divide this one, I divide this one, and this one, okay? This one though, because I already have a division by 2, I just squared it, because it's the same thing mathematically, okay? And voila, what I have done now is figure out what T of n divided by 2 is equal to. And you're like, great, are we done? Well, not really, because we still have this recursion going on over there, right? Again, we want to have on this side just things with n's and whatnot, but no t's there, and we have a t. Okay, but at least now we know what T of n divided by 2 is. So we've expanded it. So what I want to do now is I want to plug it into here. I want to plug it in there. So I want to take this stuff here and plug it in there. Okay, so let us go ahead and do that. Well, T of n is still T of n over here. Is equal to 2, and then my big space to plug in there, plus 4n, okay? And to plug it in, I'm literally going to copy and paste. And shrink it too, okay? So I start out with this right here, and I'm going to take that, and I'm going to move it there, but I'm going to have to shrink it so it fits in there, okay? That's literally what I'm doing. I'm plugging it in. All right, and that the whole thing is being multiplied times 2 because the 2 is still there, okay? So hopefully I haven't lost anyone with that. Okay, the next step is just to simplify a little bit. Let's just simplify this whole thing. I'm not going to put the t of n on this side anymore because I'm running out of space. I'll just put in equals, but there should be a t of n there. Okay, and so now I'm going to simplify by kind of multiplying this 2 times both sides and getting rid of that division there and whatnot. Okay, so one way I could do this is I could say, well, 2 times 2 is equal to 4. You know, so put a 4 there. Put a t. I can't multiply what's inside here, so this can't touch the 2 there, so we leave that as it is. But it does multiply times here, so we get 2 times 4, which is 8, divided by 2, which is going to be just 4, n plus 4n. Okay? So I can do it that way, and that's simplified. However, I'm also going to leave this 2 as 2 squared. Why? This is the part where there isn't a clear answer as to why. It's intuition. You're going to be your intuition, because remember, this recurrent relation stuff is all about finding patterns, okay? You want to find the patterns, and simplifying terms is good because it makes it easier to see stuff, but it's also bad because it hides some stuff. So because I see the fact that I'm multiplying things by 2's all over the place, it might be a good idea to leave exponents in there, okay? So that is why I'm leaving this as 2 squared instead of 4. An argument could be said that I should have left the 4 divided by 2 as well, but that one I decided to simplify. Okay? So hopefully that's not too hand waving for you. Okay? So okay, we're not done yet. We're far from done actually, but at least we solved one step of this. We went from n to now n divided by, or we went from n divided by 2 to n divided by 4. And n divided by 4 is smaller than n divided by 2. So we are definitely going closer from n to 0, but we're still not there yet. So what do? The same thing. Okay? What happens to the 4n divided by 2 again? So we did 2 times 4n divided by 2, and basically the 2's cancel each other out. So we ended up with a 4n. And we already have a 4n from before, so we have 2 of these. An argument could be said that I could also rewrite that into saying something like this. Plus 2 times 4n. So I could rewrite this piece like that. That would be okay too as well. But I haven't run out of space yet, so I won't do that. But I'll probably do that later, okay? But yeah, that's how we get that. That's fine, no problem. More questions. 4n divided by 2 is equal to 2n divided by 2, which is 4n. Yep. We need to. Yep. Okay, so you were all helping out. Yep. Cool. If you have 4n's, would it be 8n? So in theory, that's nothing I could do. I could simplify this and say that 2 squared tn. If I really wanted to max simplify this, like maximum simplification, this would be 4t n divided by 4 plus 8n. So yes, you are correct in the sense that this would be it. This is perfectly valid as well. But I'm not going that far yet because I want to be able to see any patterns that show up. And if I oversimplify, I will run into issues. So I want to simplify some, but not all, okay? This is an experimental thing that you're going to have to play around with depending on the problem. But here, we'll leave it like that just so you have it there, okay? So anyways, now we're going to do the same thing. We want to figure out what this t of n divided by 2 squared is equal to, or t of n divided by 4 is equal to, okay? So let us go ahead and do that. So little dots over here, going here. We want to figure out what t of n divided by 2 squared, or 4, whichever way you want to think about it, is equal to. Okay? So how do we do that? Well, we can either take the original one that we have. So we can either take the, can you see the laser? Yeah, you can. We can take this one here, or we can take this one here. It doesn't really matter which one we take, so just pick one to take, okay? So I'm actually going to take this one because it's closer to what I want, because it's just this and this. The difference is that this is to the first power, this to the second power kind of thing. So let's just copy and paste it in there. And we're going to zoom in because we're going to need more space pretty soon here. Okay? So there we go. However, this right now is currently t of n divided by 2, but we want 2 squared, right? So we need to multiply things times 2 again. So what that means is I gotta take this 2 and multiply it basically times 2 again. So I have to add 1 here to the exponent. Hold on. I have to add 1 to the exponent there. And then here I have to make it squared. Okay? So 2 plus 1 is going to be equal to 3. So here, let's just put a 3 already. And now that's a squared over there. Okay? So now we have basically solved t of n divided by 4. This becomes from 4 to 8. And then this became from 2 to 4. Or if we simplify this, then you would see that this just becomes an n here, right? Because 4 divided by 4 is equal to 1, right? So you could simplify it again to the n, but I'm going to leave it unsimplified for now. Okay? Just for now. Okay? So now that we have that, we're going to plug it in here. So I'm going to copy what I have above again. Leave a space for the plugging in. And then leave the 4n plus 4n, or again, you could leave it as 8n, okay? Either or. So I'm going to take this, I'm going to copy it. So I have this right here. I'm going to take this, and I'm going to just copy it in here. Let's shrink it a little bit so it fits, and plug it in, okay? So again, we got to be careful how we simplify, but I do want to simplify a little bit because I don't like the 2 multiplying 2 terms at once. So how I'm going to simplify that is I'm going to take this term and multiply times 2 here, and then this and multiply times this, okay? So this would become 2 to the 3rd power, because this is technically 2 to the 1st, so we add 2 plus 1, and then we write our t divided by n divided by 2 cubed, plus, and then over here, this becomes 4n divided by, and so here we are taking 2 squared and dividing it by 2 squared, or basically 4 dividing it by 4. So that's going to cancel out. So this would just become 4n again, actually. Okay? So that's basically what was inside, and then we just bring down the 2 other pieces that we had here. So we just bring these down here, okay? So to simplify, because I am running out of space, I am going to say 2 cubed t n divided by 2 cubed plus 3 times 4n, okay? That's the same thing, I just combined those. Again, I could simplify this. This is the same thing as saying 8 times t of n divided by 8 plus 3 times 4n. Okay, or I guess if I really wanted to oversimplify this, this could be a 12, right? 12n. That would be like extreme simplification. But I feel like there I'm going to lose things that I would otherwise not see, okay? So that's why I'm not going this far. But I'll leave it really tiny here, since some of you were asking, okay? So, are you seeing the pattern? Let's do maybe one more. Let's do one more of these, okay? If you have 2 4n's, would it be 8n? Yes, you can combine those because they're like terms. The only thing you can't do is basically touch anything that's inside of the function. This is literally a function, so you can't touch these numbers. Like, you can't mix these with stuff outside. This is its own world, basically, all right? But yeah, you can totally mix things outside and do basic algebra. So let's do one more of these. I think you're starting to see what I'm doing here. Okay? Or not what I'm doing, but like the pattern that I'm doing, basically. So let us take that and figure that one out. So t of n 2 cubed, okay? So to figure that out, again, I do what I did before. I take what I currently have, which is this. I'm going to put it here because I'm very tiny space here. And I just basically divide all of this by 2. So divide this by 2 and divide this by 2. That is basically the equivalent of saying 2t n divided by 2 to the 4, or 16, same thing. This is currently 8, so it becomes 16. And then this becomes 4n divided by 2 to the cube, which is 8, okay? So I hope that you're seeing this pattern of the numbers, right? Like how we started out, like it's just increasing that exponent, or it's just multiplying it times 2, whichever way you want to think about it. Okay, like if you look at the pattern here, you know, every time that we are increasing it, it goes n divided by 2, n divided by 4, n divided by 8, n divided by 16, and that's how that one is going. This one here is going from initially n divided by 4 to n divided by 8 to n divided by 16. And this outside one is it's not really doing much other than going from 2 to then, well, 4 divided by 2 is 2, and then 4 divided by 4 is at 1, and then here it's 4 divided by 8, so it's 1/2. So it's going in half, halves, halves. It's dividing each time by 2, right? So if I ask you right now what t of n 2 to the 4 would be, then I'm pretty sure you would figure that out immediately. You would just be like, well, you increase the exponent by 1 and you call it a day, right? Cool. Same thing over here. What is this going to become now? Well, this is just going to literally become now, when I plug in that number in here, so when I take this back and plug it in here, I'm going to even skip some steps here. Oh no, I won't skip steps for this final one. So we'll do that, and then we'll plug it in. I want to make sure everybody's on the same page with me here. Plug it in there, and bring down my 3 times 4n, and then simplify it. So this becomes 2 to the 4th, t of n divided by 2 to the 4th, plus, and then this literally just becomes another 4n from this, which we can just kind of add to the existing ones that we have here. So this whole thing is going to become 4 times 4n. So you can see very clearly between these two lines what the pattern is, right? If I ask you what the next one's going to be, it's probably going to be 2, and then this is going to be a 5 now. This is also going to be a 5. This is also going to be a 5, and so on. So, and if I ask you what it would be under 10, then this will be a 10, and then this would be a 10, and this would be a 10, and so on, right? So you basically got the pattern, okay? So yeah, that is why I am not simplifying that, because I wanted to see that pattern. If I hadn't done that, you could probably still find the pattern, but it'd be a little bit trickier to figure it out, because like we would have this 12n, which then becomes, I believe, a 16n, then 20n, then it would, yeah, it would be, I think if we had simplified it maximum, it would have gone from 8t n divided by 8. I don't like, hold on a second. I don't like how, if I'm zoomed in, it's really thick. So if we had oversimplified it, this is what the pattern would have looked like, which would have been harder to see. Still viable to see, but a little bit harder. So, you know, before that we had 4t n divided by 4 plus 8n, and then before that we had 2t n divided by 2 plus 4n. So that's what we had. So you can still see the pattern. You know, from here you would see this becomes 16t n divided by 16 plus 16n. But that's a little misleading. This one step you'll be confused because it looked kind of weird. Because the step after that, this would become 32t divided by 32 here plus 20n, right? So that's one reason here. This looks weird. This is like, huh? But really, this one's only going by 4s, as you can see, whereas this is going by squares, right? So that is why I didn't do this format. You know, I'll leave this again shrinked out into the void. But that's why I didn't do that, because I like this one better because it's easier numbers, okay? So again, this is not something that you just pick up easily. You gotta finesse with it. And obviously this is like a prepared example too, so yeah. Okay, so you're all kind of seeing the pattern. So let us plug in a variable for this pattern. So let's just put in an I. So really what this becomes is 2 to the I t times n divided by 2 to the I, because that number is the same on both sides, plus, oops, sorry, I forgot my parentheses, plus I times 4n, where I is whatever term we want, right? I is whatever we want to be. So if we want 10, we plug in a 10. We want 11, we put 11. We want 1, we put a 1, etc., etc. Okay? Cool. We're not done yet, but we're definitely getting there now. Okay? So now what you want to do is you have to ask yourselves, how many times would I need to keep doing this before I get to 0 or my base case? Okay? So how many times do I have to do this? I'm going to write this here. How many times before I get to a base case do I have to do this? I hope that's correct English for you. Do I have to do this? And we know what our base case is. Our base case is T of 1 is equal to 4, right? So how long until I get to this? Okay? That's what I want. That's the end game right there. I want this T of 1. Right now, it's becoming smaller. It's becoming really small. Like I keep, it's like dividing it by, n divided by 32. Eventually, it's going to be like n divided by like 1,000,000, and that's going to be a really tiny number. So I should get to 1 eventually, right? But what I want to figure out is what number I has to be for that to be the case. Okay? So really, what I'm trying to figure out is, if I look at my equation here. What time is it, by the way? Oh, snap. I'm running out of time. I hope we finish the example today. What I'm really trying to figure out is this right here. I want this to be a 1, right? Because if it's a 1, then bam, I'm done, because I know that's my base case. That's my miracle. Okay? So really, I want n divided by 2 to the I to be equal to 1. Okay? That's what I want to do. That's what I really, really need. Okay? So let's figure out why that's the case. That's a very simple formula. There's 2 variables, sure, but it's a very simple formula. Okay, cool. So, we can multiply both sides by 2 to the I, just so that we can get the 2 to the I out of there. So if we multiply both sides by 2 to the I, we get n is equal to 1 times 2 to the I, so just n is equal to 2 to the I. Okay? And then we pull out our logarithms, right? Because what does this really mean? Well, this is literally just saying what log of n is equal to, right? Log base 2 of n is equal to I, right? That's the same thing, because what we're saying is 2 to what power is equal to n? 2 to what power is equal to n? Well, log of something is basically asking, what power do we need to get this I, okay? So we can basically put it in this way, and then we're good to go. So we can simplify that by this, okay? So what this is saying is that log of n, as long as we put log of n as I into our thing here, so if we say n divided by 2 to the log of n, that is going to basically be equal to 1, okay? And how does this and this become that? You gotta remember your logarithms for that, okay? So, because we proved that works, then let us go ahead and plug in I is equal to log of n into our formula up here. Okay? So that is going to become 2 to the log of n times t, n divided by 2 to the log of n plus log of n times, let's make sure we don't confuse it, that's part of the log. So here, let me put the parentheses on that one just so it's obvious, times 4n, okay? But guess what? This right here, because of what we just did up there, we know that n divided by 2 to the power log of n is just equal to 1. So this really becomes 2 to the log of n, and we're doing this intentionally. That's the whole point of doing this. Log of n times 4n, okay? And t of 1 is going to be, I believe we said 4, right? Yeah, 4. So let's just plug in that 4 in there. So 2 to the log of n times 4 plus, and I'm just going to flip the 4n in front, 4n log n, okay? So now we're getting somewhere. And by the way, remember, all this stuff, it's equal to t of n or whatever, okay? So very cool. Okay, so now this is where like even I would probably have to remember my logs if I wasn't fresh with it, right? So there is a property that I showed you that says that if we have something like x log y, that you can flip that and say y log x, okay? As long as it's the same base, right? So because of that property, I can take 2 log of n and do n log 2. And 2 to 2 is just the same thing as 1, right? So this becomes just n to the first power, or just n, right? This is like that. It's like hacking, basically. Like you got to remember your logs to do this kind of weirdness. But if you do that, then you can simplify this even further and say that n times 4 plus 4n log n, okay? Because I just flipped that using that rule right there, okay? So, yeah. Yep, okay. So, let's just flip that like that so that it looks nicer. And let us go ahead and put our T of n in there, okay? Well, would you look at that? No more T of n's on the right side, and no weird numbers like the 2 to the power of log n. So there we go. We are pretty much done at this point. I mean, we could simplify this and say, you know, we could take out the 4 if we really want and say this is equal to n log n plus n. These two are the same term. I just flipped the order. But it doesn't matter because that is literally your answer. Whichever one you put is perfectly valid. Both of these are correct. So it turns out that this is neither linear. This is neither logarithmic nor linear. It's technically that n log n. So I think do we have a special term for that one? Was that the linear rhythmic one? I think that was a linear rhythmic one. Yeah. So and it turns out that this 4n plus 4n log n, this belongs to the big O category of just n log n, because the 4n here might look significant, but it's just a linear growth, whereas this one's going to grow much faster. So it kind of makes the other one be insignificant. And you can say your certificate for this is just a 4 and n greater than 1. So that would be your certificate, because now you can claim that your 4n plus 4n log n is always going to be less than some constant c log n plus cn, like that, and or c or m, whatever you want, and that's 4, right? So really what you want to just put is that this is the exact one, but it belongs to this class, because the 4n is like actually, like think about it this way. If you got this algorithm that takes like n to the 20th power plus n, and then somebody else comes in and says, well, mine takes n to the 20th power plus 1/2 of n. Sure, the bottom one's like slightly faster, but like this is so massive, this n to the 20th power is so massive that this makes no difference. It's like, yeah, this is like, okay, sure, it takes a little longer, but like it's already into the 20th power, right? So that is why we don't really care about these smaller things. We just look at the bigger term, and that's the one that defines the asymptotic complexity, okay? So, yeah. What's stopping us from multiplying 2 in the beginning instead of dividing by 2, then solving for t of n? So you're saying we want to multiply times 2? Okay, so we can try that, but we're not really going to get anywhere from that, because so what you're saying is, if I have this and I multiply times 2, then I say t of 2n is equal to 2 times t of n plus 8n, right? Okay, but then what? We still got this 2 of n to work with, right? And we don't know what this is equal to. So that doesn't really get us anywhere. We want to ideally either go towards 0 or go from 0 to n. We don't want to make it a bigger case because we don't care. We only care up to n. We don't care above n really. So that's why that doesn't really work. But yeah. So all of this effort just to figure out that this is n log n. Okay, this one's of course far more complicated, but this is as complicated as they'll get in this class really. So yep. This is some hardcore stuff, so don't feel bad if you're like a little bit confused. It's not really easy. Next time I'll show you the 3 method really fast, and then maybe we'll do a little bit of master theorem, and then after that we will move on from this and never see it again. But whenever you do your assignments, you want to try to use this stuff to figure out what the asymptotic complexity of your code is. So don't make your code so complicated that the recurrence relation becomes really complicated, right? You don't want to do that. You want to make a simple code so that you can simply solve the asymptotic complexity. Because as you can see, if you make your code complicated, then trying to figure this out will be even more complicated. So that's real motivation for you to not overcomplicate your code and not overuse recursion, basically. Yes, so this is the longest question in the test, but you know, you can use the master theorem on the test and you'll see that takes a lot less time. Because yes, well then again, I mean, you could have done this a lot faster if you know, if we weren't explaining it. Like try doing this example again at some point before the exam and you'll see that you can do it much faster as long as you actually remember it. So, but yes, I was expecting us usually to take an entire class period to do one example. Which, yeah, it's not just for this. When we do like Dijkstra's, an example will take us like 40 minutes, but it's okay. I better one good example than a bunch of half-done examples. Actually, we did 2 examples today, so there's that. There should be a lot of time in the test, so you should be okay, I hope. But yeah, that's it. That is the entire class, everyone. So, yeah. Thank you all. I'm going to stay online because I guess I'll not just stay until my 2:02 one, but I'll probably switch my camera off for a minute or something, get like a restroom break or something. But thanks for coming. Have a good weekend, everybody. And I'll figure out assignment due dates and whatnot, because, you know, so that it links up to this stuff. Okay? But, yeah. See you all later. You get them automatically as long as you're logged in. So you should be able to see them. Let me stop the recording on YouTube really fast. So give me 1 second.